So hi, my name is Momjian. Work for Enterprise DB. I'm one of the working members. Been working on Postgres since 1996. I'm excited to be giving this talk. And frankly, I don't know about any of you, but this is, in terms of quality of talks, this PG Con has been the best PG Con that I can remember. Pretty much, I don't know, forever, maybe for the last 4 or 5 years. So I don't know, the quality. There have been some previous years where there was one talk that just like knocked me out of my seat. This one, and virtually every talk I went to, very high quality, very pointed at exactly what I was interested in. I'm not sure, I called some other people, they sort of felt the same way. So it'd be interesting for organizers to see if we get that feedback. So please do give us feedback. There's some things that we can do to improve. I know we're all interested in finding that out. So today, what I want to talk about is effectively the Postgres Query Optimizer. This is a very interesting topic to me. In fact, this is the reason I got involved in Postgres, because in 1996, I had been writing financial applications for 7 years. And you know, after you write financial applications for about 7 years, you're really not learning a whole lot anymore. And as a professional, I felt like I wanted to learn more, I wanted to understand more about what I was doing, and because I was writing database applications, occasionally I would get to look inside of the database to see how was a query that I sent to the server actually executed. How is it making its decisions, and how is it returning those results as efficiently as possible. And at that time I was using Informix and Ingress, and I was not able to see really inside of how they made those decisions. I could kind of see a little bit of the plan that came out, if you're familiar with those products or other products that generate a plan, but I couldn't actually look at the code or understand the process it was using to make those decisions. And one of the real attractions of Postgres, and one of the reasons I got involved in sort of starting in internet development in 1996, was because of that openness of code, because I could actually understand it. Now, I'm not going to actually be talking about the internal code of what goes on in Postgres too much today, but what I am going to do is kind of walk you through basically how Postgres makes those decisions and give you a little more appreciation of what is going on inside that server. I know a lot of people are sort of keen on, you know, non-relational systems these days and sort of looking at things that don't have an optimizer, but I think one of the things you're going to get out is understanding how much of that optimizer helps you as an application developer not have to worry about a lot of the intricacies that you normally would have had to work and deal with before relational systems came around. So, you know, simply when you're writing an application, as you would be here, usually you have some kind of interface layer that sends the query across to the server and then sends the result back to the interface layer and then up into the application. We're going to basically be focusing on what happens inside of that server, that part to the right. So internally, Postgres effectively has a sort of an internal flow that goes through to figure out how to execute a query. And in fact, the most important part of that flow is what we call the optimizer or the planner. Now that's not the first section that actually occurs. When a query comes in, the first thing that happens, rather than coming in from the top here, the first thing that happens is the statement's parsed. It's broken down into words, and then the words are then treated as tokens or lexemes, which are then passed to something called a lexer, which effectively generates actions based on the pattern of tokens or keywords that come into the parser. There's then a traffic cop in Postgres, which figures out if it's a utility command or not. If it's not a utility command, it goes into something called a rewriter, which is where we handle things like views and rules. Down after the rewriter is that optimizer. Effectively, what it's doing is trying to figure out how can I get that user the results as quickly as possible. And what comes out of that execute optimizer is something called a plan. The plan effectively is sent to the executor, and that's the part that actually executes the query. So this is sort of the map maker, the one who lays out the plan of what we're going to do, and that's effectively passed into the executor, which is really just something that follows whatever plan came out of the optimizer. So it's really just executing a recipe that's come out. So we're going to focus on that optimizer, what I think of as the brains of the system. What things does that optimizer have to do? What things does it have to decide? There's three major areas that it has to make decisions on. One, what is the scan method that's going to be used to get at the data? And I'm going to go into specifics about what scan methods are available in Postgres. Secondly, what join methods are going to use. We're going to show you specific examples with diagrams and show you exactly what join methods are. And finally, join order. That's sort of figuring out how to join table A to B and then C, or do I join table B and C and then A. You know what I'm saying? Different orders of bringing things together. And I'm going to show you specific examples here. Now, you might not be using Postgres, or you might be using Postgres plus some other relational systems. These concepts are very generic. So in most systems, most relational systems, you will see the same concept. The terms may be slightly different. There might be a couple other things that aren't there. These are very generic relational concepts. So, first thing, scan methods. There's basically three types of scan methods supported in Postgres. And again, deciding which one to use is something I'm going to show you in a couple minutes. The first one is called, but let's first, before we do that, let's set it up. So first what we have to do is we have to create a little like temporary table so I can illustrate all the things I'm going to talk about. So effectively what I've done here is I've just run a little query that goes into the system catalogs and just pulls out some of the relation names in the system. And then what I did next is I took the relation names and I chopped off just the first letter. Just chopped off everything after the first letter, just got rid of it. Okay? And then I created a temporary table with this contents. So effectively what I did was I took the system table, then I chopped off, I just took the first letter of the relation name, and then I put a bunch of junk at the end and I created a table called sample, and I put an index on it. That's all I did. Okay? Because I'm going to use this example for the next probably 10 slides, and this can kind of give you an idea of how this is going to work. Now, if you want to run this yourself, the part in pink here is actually, this is actually the SQL. So if you want to download this, you can run it, and you can actually see it running on your terminal, and you can actually see the exact same output. There are a bunch of slides on my website. In fact, I'm sorry, I forgot to mention it. And the reason I didn't mention it now that I realized it is because it's chopped off at the bottom. But effectively, if you go to this website right here, and get rid of that rest of the part there, this right here. If you go into presentations, there's probably this presentation is there, and then there's 30 other presentations also there. They're in PDFs, and you know the bottom isn't chopped off. So if you're missing the bottom there, you can definitely check that out on that website. So this is the temporary table we're going to use. And then we're going to also use a function that I used a little bit to display things a little better. Again, this is also in the SQL file. So let's see, what does this file look like? I created a temporary file, and I made a little query, and I said, just tell me what this looks like, this temporary table. So effectively, I have, I think there's about 253 rows in this table. I can tell when I created the temp table. 199 of them have a P, just the letter P in it, and then another field which has a bunch of junk on it. I have 9 of them, which is an S, and then 8 of them, which are a C, and then down here I have 1 row, which is an I, and 1 row is a K. And the reason I created this is because it gives me a nice distribution of a variable kind of case, where I've got 1 letter, which is really common in the system, a couple letters are really common, and then I've got 2 letters, which are a bunch of letters, which are very rare. And this is the type of case that you have in relational systems. This is one of the areas that Optimizer does very well, is it kind of can adjust things based on how selective your data is. And I'm going to go into how that happens in a minute. Okay? So, what do I mean by selective? Okay, so if I just do this query right here, and I say, give me a P, okay, what it actually ends up doing is something called an index scan, which, like, okay, So what if I use, that's my most common value, right? So what if I do a D, which happens to be kind of in the middle here, I got 4 of those. And that's also an index scan. And then what if I do a K? Well, that's my rarest value, and it's doing the same thing. I got an index scan for all 3 values. For my most popular value and my least popular value, they're all returning the same thing. Well, why is that? Well, the reason is because I don't make statistics on the table. What statistics are we have a special thing called optimizer statistics. And the optimizer statistics tell the optimizer how common certain letters are or certain values are within a table. So normally there's something called auto vacuum, which will run and analyze for you, but that runs like every minute, so I might not want to wait for the minute for it to run. And in this case, I'm using temporary tables, which auto vacuum can't even see, so that doesn't help me. So I've got to run to analyze myself. I just went and I ran that analyze right there at the top. And as soon as I run that analyze, you see a change right away. That key, which used to be an index scan, is now a sequential scan. Okay? And a sequential scan is effectively saying, start at the beginning of the table, read all the rows to the end of the table. Very straightforward, just, read everything. Very easy. This is the easiest one to understand. Now, why did I choose a sequential scan? That's because we showed up here that 78% of our rows were P's. So, if 78% of your rows are P's, it doesn't make any sense to do all sorts of index lookups to somehow eliminate 22% of your rows. Doesn't make sense. So we're just going to read straight through the table. That's the way to go. What happens if I do a D? Now, D, I do 4 of those. Okay, D ends up giving me something different. It gives me what's called a bitmap heap scan. Sounds kind of weird, but what it effectively is doing is it's going through the index and it's creating a bitmap that tells me where can I potentially find matching rows in the heap. And I'm going to put a 1 every place I can and a 0 any place I'm not going to find it. So effectively what I do is instead of doing 4 accesses, I'm going to go through the index once, it's going to make a little bitmap, and then I'm going to walk through the bitmap. Now this is probably overkill for this case, but again, because there were 4, it decided to create a bitmap and then use that to kind of aggregate all the lookups into the heap. If I do the K, which there's only 1 of, I actually get an index scan, straight index scan, with no bitmap, because there's no need for a bitmap, because it knows there's only 1, or at least the statistics are telling it that there's only 1 map. It's going to go through the B tree, it's going to find the row, we're done. Okay? So this is the first example showing how the optimizer statistics are effectively changing how we go at our data. All right? And again, as an application developer, you don't have to worry about, am I querying something that's very common or am I not? And this happens all the time. If I'm in Ottawa and I'm querying all my customers in Ottawa, well, I probably have a lot of customers in Ottawa, so I'm probably going to just do a sequential scan of all my customers. But if I have an index on the province, and I try and query somebody in Manitoba, which I actually know is a province of Canada, amazingly, from my education years ago. Am I right? It is one, yes. Don't hear about it very much. I'm not sure why. But if I wanted to see how many customers I have in Manitoba and I've got an index on province, odds are I'm going to use an index there. Because there's probably a couple, because I don't think there's that many people in Manitoba. Anybody from Manitoba here? Somebody, I'm disappointed. Anyway, somebody can probably give me a good history lesson after and tell me what is there. Because I'm always fascinated by Canada. But anyway. I think it's really a really great country. So, let's take a look at a better description of this, okay? So what I did, I just did some random letters, right? I just did 3 letters and I kind of showed you. So what I did is I created a little kind of query here, and I'm actually using a little function that I use. And I'm getting this output. But if I kind of query it a little differently, again, all these queries are in an SQL file, I get this. is the quintessential slide for the presentation. Because what it's illustrating is that as I go from the most common values at the top to the least common values at the bottom, the optimizer is automatically changing the type of access method it uses to get the data automatically with me not having to do anything at all to the query itself. Okay? And this is all driven by the analyzed statistics that I created early on. Are there any questions so far? Yes, sir.
So I would have expected the sequential scan to only be on that first row. Why is it doing for 9 and 7 but not 5?
So the question is, why is the sequential scan actually doing it not only for 199, but all the way down to the R, which is number 7, and then down? That is a very common question, because most people think that the index should be used if it's selective, sort of. So they'll basically say, well, you know, I understand if 78% of my rows are P's, I probably don't want to use it there. But you know, if it's 30%, I think that sounds pretty good. But then we realize that the index has a root page and then different sub-pages to get to the thing. And then you realize that, that you're going to have to randomly go through, you're going to have to randomly hit the heap pages. Now, of course, if you use a bitmap scan, you can kind of do them in order, but you're going to be hopping between. The bottom line is that random I/O is really slow, and sequential I/O is really fast. Okay? So the sort of dirty secret is that, like, an index almost has to be like under 5% selected before it starts to be used. And that's effectively designed because of the way that the costs are set up in Postgres and the type of the way we know we have to do multiple reads to get through that index to get to the row. Whereas we do a sequential, we know we're just like, not only are we reading like straight through, but the kernel is prefetching ahead of us because it knows we're going sequentially. So is 5% a good rule of thumb at any scale? Not really. I mean, the number actually goes down as the table gets bigger, but usually 5 to 7% is about the number we're going to see. Now, that kind of breaks pretty close because the 5, I said there were 250 rows in the table, so 253. So a 5 is what? That's 2%? Yeah, so that's actually breaking, I would say, much lower than that. Now the 7 is probably around 4%, 3.5, something like that. So again, I think the number's breaking a little even lower than 5%. I'm maybe even generous. And it continues to surprise me how low that number really is. Now, if you think I'm making that up, which you could, okay? Well, actually, the way I'm doing it is going to fake it, but I want to show you something. What if I tell it, what if I force it to do an index scan? I say, I don't believe you, optimizer. I am going to turn off sequential scan with that top line. I'm going to turn off bitmap scan with the next line, and I am going to force an index scan. I'm sorry, I'm going to turn off bitmap scan and sequential scan, and I'm going to run that again. And what you see is that when you look at the cost, the cost down here was around 12, it goes to 15, it goes to 90. Ends up when you get up here at 39. The original output, which is this one, again starts at 8, goes to 11, but it really doesn't go any, it goes up to 13. Okay? Now, if you think the optimizer is doing something wrong, you can turn it off. We're using these commands at the top, and you can rerun your query and time it and tell us, are we wrong or not? Okay? In almost every case when somebody actually, we have an FAQ item that even talks about, why is my index not being used? This is a very common question. And it actually shows you these commands, how to turn it off. It says run it with it, run it without it, tell us what you get, and the questions magically disappear. It is amazing. We put something in FAQ, in 6 months, you don't get any questions anymore. Is the system perfect all the time? No. But overall, the costing is pretty accurate, and we don't seem to have too much, it's almost counterintuitive how low that breakpoint is. And you can adjust it if you have SSDs, page cost. So there are some things you might need to adjust if these numbers, if these estimates are wrong. But in most cases, it gets it pretty close. And it's all question over here.
The numbers on the chart, were they were estimates or the actual measurement?
Yeah, you know, that's what I was getting to, but I'm actually cheating. And the cheating is that these numbers are actually the costs that the optimizer is giving us. These are not actual execution times. So I could have expanded this and kind of done the full execution time on this. I didn't do that. Partially because the numbers were floated around, and then also partially because you start to get caching effects when you have multiple, because when you run it once, it's not in cache, when you run it again, it is in cache. So the numbers kind of tend to float around, and it's kind of hard to get really accurate numbers in that case. Yes, sir?
Do we find that the percentages actually increase if the table was much wider?
So do we find if the percentages increase if the table gets much wider? In fact, there's what you can't see over here, and maybe I do need to change my resolution. I don't know. What resolution is this thing? We don't know. Anyway, what's over here is actually a width estimate. So the optimizer knows how wide the row is, an estimate of how wide the row is, and it will actually adjust it based on that. So a shorter row will have a tendency to be looked up differently. Other questions? Yes, sir. Oh, ma'am.
Does the optimizer take into account a clustered index?
Does the optimizer take into account a clustered index? Yes, it does. When you issue the cluster command, the next analyze operation will actually sample the cluster ratio for the table. And because the cluster is not maintained, you have to recluster it, the cluster remain. Effectively, every time an analyzer is run, there is a special index that is marked as the clustered index in the system table. And it will actually randomly sample and will update that amount of clustering ratio in the statistics, and that will be used to determine how localized a lookup is, particularly if you're looking up like a P or a D, where you think, is it spread in 4 different places on the table, or is it maybe all in one page? So in fact, it's not only do we record it, but we actually keep it updated, and the ratio will decrease as the clustering gets dispersed within the table. Other questions? Okay. Oh, I'm sorry. Yes, sir.
I was just going to say that I think the table is so compact that the choice of scan doesn't really matter for this case.
Yeah, this
It's like everything fits on one page.
he's saying it's kind of contrived, and I will admit, yes, that's true. Normally, I would take a huge data set and run it through this thing, but then the problem is the numbers are so huge that you can't really conceptually get that. Yeah.
Except there's a page for the index. So you actually have 2 page sessions.
Yeah, but it's already in memory stuff. Yeah.
So, will the planner to decide whether it's sequential scan or bitmap or index scan, if you've got an index that is actually indexing 2 or 3 columns, will it consider all those values? Like, does the statistics have combinations of values?
So the statistics have combinations of values. But if you have a multi-column index, does it look at the combo of that? Unfortunately, fortunately, it actually indexes every column. So whether the column is in an index or not in an index, it's going to index them all. Because a lot of times, you're going to say A equals 1, B equals 12, and that B, although it may not be indexed, would be very important, and we need to know how selective that is to determine how many rows are going to come out, which is actually part of the later part where we talk about how we join data. So we index all of them. We don't index any of the columns specially. One of the big flaws in the Postgres optimizer is the lack of information about correlations between multiple columns. We've talked about that. It is on the to-do list. It's something that we have not really understood how to efficiently generate such correlation and use. That is one of the flaws, I think, one of the areas we have to improve is the correlation between columns. Sometimes if you say this is 1, this is 12, that may be a very rare case, and we're gonna look at each one individually, which is.
So we should kind of get limited benefit out of multi-column index.
No, so the question, do you get limited benefit on multi-column index? You still get a big benefit from them, it's just that you don't, the statistics are perhaps not as smart, but you're still gonna be able to look up and filter across multiple columns. In fact, if you have a column index of A, B, and C, and you give us A and C, we'll still use the index on A and C in some trickery that we have to kind of span gaps, and I'm not even going to, but multi-column indexes are certainly very good.
However,
They're not as useful for planning,
Well,
but
that's the thing, it doesn't select the index because the
It,
planner.
yeah, but it probably will, it probably still will. And the other thing that you get into in this case is that none of these numbers are perfect.
Right.
Well, they're all fudgy numbers. And in fact, even if I had a perfect number today, right now, 5 minutes from now, it would be wrong. Okay? So the point is that these estimates, they don't have to be perfect, they just be good enough to pick a plan that's probably closest to the best plan. So that's probably good enough. Trying to get perfect numbers wouldn't be efficient, and B would be probably very useful.
These don't have a lot of competing indexes that have similar sets of columns.
That's correct. The more indexes you have, the more possible combinations of best work.
Yeah.
you're right, but we also have, a lot of Bruce never got in his talk is the bitmap, right? Bitmap that we have, where you can take, so the problem with the ABC index, right, is that you want to look up ABC, you decide it's useless to you.
Sure.
Right? But what you do instead is you create independent indexes on A, B, and C, and then we're able to actually use the index on A and the index on C at the same time.
Right.
You kind of like this is showing they're combined together.
Using bitmap
So
stuff.
you can combine it together.
And so that's where you would generally, want to, that's what you want to generally do, I think. I mean, there are specialized cases where you will want an ABC index, uniqueness constraints, and things like that. And yes, it can be useful for, it'll be faster than bitmaps, the bitmap-based stuff, but at the same time, if you're not sure exactly what the query pattern is going to look like, you're not sure that you're always going to be querying with all 3 columns, you ought to be creating the indexes independently.
Okay, now I'm going to stop the discussion there.
Okay.
Because we do want to finish the material. So the second thing that we want to talk about is what we call join method. Again, this is fairly common for most of the relational systems. There are actually 4 different join methods, or 3.5 different join methods you can use. The first one's nested loop with 2 types of that. Second one's hash join, and the third one's merge join. I'm going to show you examples of that and diagrams for each of those. Okay, so we're going to have to create another sample table. This time I'm going to pull some rows from PG proc that happen to be numbers. And I'm going to create a sample 1, which pulls rows from PG proc. And then I'm going to create another table called sample 2, which pulls some OIDs from PG class. Again, nothing super exciting. You can, this is in that SQL file. I'm going to start out with no indexes and no statistics. Okay, so I'm starting with absolutely the worst case that we could do, right? So if I do this query with a where clause that's comparing sample 1 to a constant, and I'm doing sample 1 to sample 2, I get what is called a nested loop with a sequential scan and a sequential scan. It looks just like this. It's as bad as it looks. It means compare every row to every other row. Now the only reason this could be a win is if you have very small tables and there's no setup required. Okay? So very small joins potentially will use this because it's super fast. Right? And it looks like that. What if I restrict sample 2 to be greater than some number, not equal, greater? I get what's called a hash join. Okay? And a hash join effectively says take one side and hash it, and then do lookups from the other table into that hash. This is super, super popular. It's sort of the vanilla bean ice cream of databases. They love doing this. Okay? Middle of the road kind of join. And as long as one of the tables fits in memory, you're good. Okay? It looks like that. But what if I do a join with no restriction at all? Then I get something called a merge join. And I have to sort in fact, in this case, this is what a merge join looks like. It says, take the first row of the first table, compare to the first row of the second table. Then, if that matches, you go to the first row of the first table, compare to the second row. If that doesn't match, then you can move down and compare the second row to the second row, and then the second row to the third row. If that matches, keep going, second row to the fourth row. If that doesn't match, go down to the third row of the first table, you got a match. What you're effectively doing is you're walking the two tables simultaneously. Okay? So you're kind of advancing the one table and then advancing the other table, kind of moving down. One scan through each side of the table. This is great for large tables because it doesn't have to fit in memory, and you're not multiple scanning it as you would, in a nested loop. Okay? So this is really, really useful, and again, you see it for big results. And it looks like that in pseudocode. Now, what if I change the order? Because before I did sample 1 join sample 2, now I'm doing sample 2 join sample 1. Doesn't matter. Does not matter. In most cases, the smaller relation, the more restrictive relation, is on the outer side, and then you just run your merge join the same way. Now, if I add statistics, okay, I'm going to expect to see a change, because now the optimizer has some clue of what's going on. It has some clue of how many rows are there. It has studied or it kind of knew how big the table was. It didn't know how many rows, and it knows how selected some of the constants are. So, for example, here now, this one used to be a merge join. This join, remember, with no where clause, this was a merge join. Now it's a hash join. Because it realizes, these tables aren't that big, it's going to fit in memory. Now I have statistics to prove it, I'm going to do a hash join. Okay? And if I do, even if I do an outer join, which you think couldn't use a hash join, we can still do something called a hash left join, which is kind of weird. Not a lot of databases support it. We do. New in Postgres, not all. Okay? What about cross join? You've probably never seen that before. A cross join is basically saying join every row to every other row. And what possible optimizer join method could this use? It's got to be the nested loop, because that's the one that compares everything to everything else. There's nothing else that can do a cross join. So you can even see when you do something that you would think would use a cross join, in fact, does a cross join. Now, let's layer something else on top. Let's create an index on both fields. So now we create an index on both tables. I'm sorry, not both tables. Both tables. And again, we're going to get some different decisions from the optimizer that we didn't get before. So here we have the case where we're comparing it to a constant. And what now happens is we saw a nested loop, but the nested loop is much faster because we're now able to look up the 33 with the index. So instead of having to compare every row to every other row, now I can zoom right into each table and say, just give me the 33s, I don't care about the other rows. And it looks exactly like this. So it basically uses the index to find all the 33s here, and then it joins it using the index lookup to all the 33s on the other end. So again, a lot of people see index nested loop there. Well, if you got an index there, nested loop isn't necessarily bad, because you're not joining every row to every other row. You're just joining every row that matches the index, every other row that matches the index. And again, this is a double index scan. You can get cases where you have a sequential scan here and an index scan here. The point is you want the index scan on the inner side, on the bottom. Whether it's on the top or not, it's better to have it, but you don't have to have it. And again, if you don't have an index at the bottom, then you're going to be scanning every table, every row to find a match, and that can get slow, particularly for large tables. Okay? That's what that looks like. So, what about a query restriction? Now, this gets a little more into statistics. If you remember way back when we started, 25, 30 minutes ago, I put some junk in the column. You remember that? And I put like 200 X's. The original table design I did, I'm back to this one where I created it here. Right, so this is 250 X's here, and the second column is 250 X's here. So if I go in and I say, okay, I'm going to put X's in there. And the optimizer actually know that there's no A's there. But you know, it kind of takes my word for it, and it says, okay, I'm going to assume there's one A matching here, and I'm going to assume there's one A matching here. Statistics tell me 0, but I'll assume 1. Okay? So it even knows for a non-indexed column how selective that is. And it does affect what it ends up doing in terms of joins and in terms of index lookups. Okay? If I do the same thing but I ask for X's, that's completely different, right? Remember, nested loop it uses when it knows that. I'm not going to get any rows out, it's going to be small, right? But when I'm doing this with the X's, then it says, okay, I'm going to do a hash join, and I'm going to pull my pants. This is going to be, we're going to get some rows here. And you can see the row counts are pretty significant. Okay? So, again, it knows a lot of stuff and it adjusts it. Last thing I want to cover before I take questions is the idea of a limit clause. Many of you have probably seen the limit clause, originally came from MySQL, very common now. It effectively allows you to tell the optimizer how many rows you want. Now, before the limit clause, people would use, they would effectively use cursors. If you've ever used cursors before, the reason we don't recommend cursors is because cursors effectively tell the query to run, but they don't really tell the optimizer how many rows in the future you're going to ask for. But when you use a limit clause, you're telling the optimizer, I want you to run that query, and I really am telling you at the time you get the query, not some later time. At the time you get the query, I only want X number of rows. So here we're running the same query again, no error clause, hash join, it knows it's going to return a lot of rows, 260 in this case. However, what if I say limit 1? I say run that query, but optimizer, I really only want 1 row from that. All of a sudden, the optimizer can use an index that exists on the table, can pull things up, and instead of hash join, now I'm doing a nested loop. Okay? What if I ask for 10 rows? Still a nested loop. It still thinks it's faster to do a nested loop with an index scan, pull those rows based on the order by, okay? What if I say 100? 100, okay. Now we're back to where we were before. So you see what I'm saying? 1 was a nested loop, 10 was a nested loop, 100, okay, we're back to hash join. Now I think I'm returning 2 many rows. So again, another example of how the optimizer is sort of using those smarts to adjust what it's doing to figure out basically how to get the answers to you as quickly as possible. Okay? So that does finish my talk.